All right, we're going to give this a try here. Here are some questions for you to think about first. So we would have done these in class. The first one is, what's the general equation for the electric field strength? So what's the equation we came up with for the electric field? Maybe we'll do a Zoom on this. Maybe we'll try Zoom sometime soon here. It'll be longer, but it'll be more interactive. So I'll try to see if I can get that set up. This is the general equation for electric field. The electric field is the force on Q naught, a little test charge you put in the field. That's this. The force, the electric force on Q naught from the electric field divided by the charge of Q naught. What is the equation for the electric field strength created by a point charge? So if it is a point charge or a spherical charge, then we can use Coulomb's law to find Fe. So Fe would be K Q1 Q2 over R squared, but it would be K Q source Q naught over R squared, and the Q naught would cancel out. I showed you that in the video yesterday. So we would do K Q source Q naught over R squared, all divided by Q naught, and the Q naught cancels out. We get K QS over R squared. And it says, when is the first equation true? Well, the first equation is true all the time. It's equal by definition. So you can always, this is always true. It may not always be the way to calculate something. If you want to find the force between 2 point charges like we did before with Coulomb's law, I would not use that equation for the force. And if I'm given a point charge or a spherical charge, it might be faster to not calculate this or try to calculate this, just to calculate it using this. E equals K QS over R squared. And we'll look at a problem later like that. When is the second equation true? Well, this equation is only true when you can use Coulomb's law, because we used Coulomb's law here. So if it's only true when Coulomb's law is true, what are the conditions on Coulomb's law? The conditions on Coulomb's law were when the charges here are point charges or spherical charges. So only for the field around a point charge or a spherical charge. Q naught will always be like a point charge, a little tiny point charge you put in the field. But if QS, the source charge, is a point charge or spherical charge, then we can use Coulomb's law, and this equation here will be accurate. What is the direction of an electric field at a given location? What is the direction of an electric field at a given location the same as? So pause the video. How do we define the direction of the electric field? So I'll give you a hint. The electric field points in the same direction as something else, as something gets pushed. So the electric field is in the same direction as a positive charge gets pushed or a negative charge. We could have picked it either way, but we picked a positive. So it's the same direction as a positive charge at that location would be pushed. Okay, so we would have taken out a new piece of paper and looked at this. What direction is the electric field at Z? So we're going to forget about this charge for a second and just look at this one. If I call this like charge 1 here, I think I can draw some stuff here. If I just call this 1, I'm going to call this over here charge 2. What direction is the electric field from this charge, Q1, at Z? Well, we would pretend to put a little positive charge there, and I erased all of them. Rats. 1, 2. Pretend to put a little charge, positive charge there, and it would get pushed either to the right or to the left. And it would get pushed, if it's a little positive charge from Q1, it would get pushed to the right. So we would have an electric field that way. And then from 2, we would have an electric field this way. And we would take those and we would add them together. So something like to the right and up makes up and to the right. So the electric field would be this way. And if we really wanted numbers, we would use the Pythagorean theorem and inverse tangent to find that direction of the electric field. We would find the electric field using K QS over R squared if it looks like a point charge or it looks like a spherical charge. Okay? But we're just looking for general direction that was up and to the right. So now let's try this one. So I'm going to have you think to yourself here, what direction is the electric field if the situation looked like this instead? So now we would say, well, it's at Z, if this is 1, if this is 1, then it would get pushed, a little positive charge at Z would get pushed to the right again. But now, forgetting that charge, at Z, it would get a little positive charge at Z, or my little Q naught pretend to put a little positive charge there, it would get attracted downward. So the direction of the electric field is the same direction as a positive charge at that location would get pushed. So this is not really the direction of a push, it's the direction a positive charge would get pushed. So this is the electric field from these guys. So this is, E1, this is E2, and if we were to add those together to the right and down, we would get down and to the right. So again, we take these arrows like this and like that, and add them, and the electric field this way would be down and to the right. Okay? What about something like this? Get my arrows back here. So now at Z, if we call this 1 and this 2, let's do 2 first, the electric field from 2 at point Z. You pretend to put a little positive charge here. Which way would a positive charge get pushed if it were right here from this guy? Will get pushed, it would repel, get repelled by the other guy and get pushed straight down. So the electric field from this one is straight down. The electric field from this one, though, is not straight down. It's kind of this way. However, what would the result of those two be? Well, we would have down, and then we would do from there down and to the right. Okay, and the resultant would be from there to there. But down and down to the right still make down and to the right. I should have probably drawn this one a little bit more down. But so how would we get that answer? Suppose we wanted to do math with it. How would you calculate the electric field at Z? So I'm going to pause here for a second. What would we do to get the numbers right there? So actually, let me show you how you would solve this. Now, I don't really expect you I'm not actually asking you to do the difficult part of the problem, but you should be able to catch the first part of the problem. And let's see if this will focus for me here. There we go. So I drew a picture of the problem, just redrew it. And what we're going to do is find the electric field here from Q2 first. So what direction would it be? If this is plus, what direction is the electric field here from Q2? Well, if we pretend a little positive charge there, it would get pushed down. So E2 is that way. But then the electric field from this one, I should have drawn that over the other side. E1 is going to be this way. It would get repelled from Q1. And I need to draw a bigger picture of this later here. But the numbers look like this. K Q2 over R squared. This is 10 to the 9th and 10 to the minus 9. This is 9 divided by 9. Turns out to be 1 Newton per Coulomb. Tried to make the numbers easy. The second one is this electric field from Q1. This distance is what? How far is it from there to there? I put 4 here, but that's actually wrong. Because that distance is not 4. 4 is from there to there. So what is this distance is 3. This distance is 4. If we do 4 squared, it's 16. 3 squared is 9. 16 plus 9 is 25. Square rooted is 5 meters there. So this bottom part is 5 meters, and then you square it. And then we're going to multiply this out. These guys go away, and we get 18 divided by 25 equals 0.72 newtons per coulomb. All right, and then that's really what you need to be able to do. You need to be able to find the electric field at a distance away from some point charge or spherical charge. You also need to be able to add perpendicular vectors. These turn out to be not perpendicular vectors. If we were to draw this direction, this would be straight down, but this one would not be straight down. It would be somewhat this way. So to save time on the video, well, I'll show you some of the setup here. What we're going to do is we're going to take this vector right here, and it's down and to the right. And I need to figure out how much down and how much right it is. Okay, this is all on the, say, negative y, if we want to put axes on this. This is not on the negative y. It's partially negative y, partially positive x. So if I were to draw this vector, big E1, I'm going to figure out how much of it is to the, say, positive x direction, if we call it to the right, the positive x. What's this? What's E1x? What's E1y? if this is E1, and E1 is 0.72 newtons per coulomb, well, E1x would be E1 sine or cosine of this angle. I should not have started writing. So it depends. If we want this angle, that angle there would be this angle here. This angle here, this is a vertical angle, right? So this angle there. I don't really want that angle so much there, but I guess I can use that. This we knew was 3, and we know that this is 4, and we know that this is 5. And if I have that angle here, you can find this angle. You can go ahead and use trigonometry if you want to. Take out your calculator, do inverse sine or inverse cosine or inverse tangent of something there, say inverse tangent of 3/4. And that angle is like 36.8 degrees or something like that. But here's what we really want. I want E1 actually cosine of that angle. And the cosine of this angle, if you look at it, this is the, well, if we go up here, this is the 4, this is the 5. So the cosine of this angle is the same as the cosine of, the cosine of this angle here. These angles are the same. And the cosine of theta is 4/5. So if I want this, this is 4 and this is 5. So it's E1 times 4/5. So I'm just going to take 0.72 times 4/5. That is E1x. And E1y will be E1 sine theta. And the sine of this angle is the same as the sine of that angle, which is 3/5. So that's E1 times 3/5. So 0.72 times 3/5. And then we would take those, we could draw this, but see what we're going to do is we're going to take this. This is E1x and E1y, but we still have this E2 was all straight down. So I'm going to draw this. E2 was an extra 1 Newton per coulomb. And I believe this here is 0.576 newtons per coulomb. And this one here was 0.432 newtons per coulomb. And so what we would do if we wanted to do this whole calculation is we would take this as 0.432 and this was 0.576. We would make one more big triangle right here from where you start to where you finish. And its sides look like this. This side is just the 0.576 newtons per coulomb, and this side is the 0.432 plus the 1. So this much plus that much. So that's the 0.432 plus 1 is 1.432 newtons per coulomb. And then we would use the Pythagorean theorem and inverse tangent to find our answer.